introduction, Cheyenne, and thank you to both Cheyenne and Mateo for the invitation to speak here at JIPS. So today I'm going to be telling a story which involves all four of these things in this title. This is, the main player in this story is going to be p-adic random matrix theory, and we'll see that it relates also to random groups, that there are structural analogies with singular values of complex random matrices, and that you can sort of study this whole business very nicely with symmetric functions. The new results which I'm going to share are contained in this archive preprint, which I've listed here. And so, if you want to take a look at that after, everything I say should roughly be there. Okay, so also, of course, if you have any questions, please just stop me, shout them out. This is a small seminar. You shouldn't have to, hesitate on that. Okay, so first let me just, introduce p-adic random matrices and what we do with them. So let's just fix a prime p for the whole talk. And these random matrices are going to be over this field qp, which, like the real numbers, it's some field which contains q. And how do you get the real numbers? Well, you take q, and then you have this absolute value, and you complete, so you add in limits of arbitrary Cauchy sequences. In particular, among these Cauchy sequences, you have, successive truncations of a decimal expansion. And so usually when you think about a real number, you're just thinking about this decimal expansion. To get the p-adic numbers, qp, you do the same thing. You complete with respect to some norm, but it's a different norm, which I've written absolute value sub p. And it's defined by if you have a rational number, you can write it as some power of p times a fraction co-prime to p. I should say a non-zero rational number. And then you just define the absolute value to be p to the minus n. So rational numbers divisible by a high power of p are very small in this norm. And similarly to the decimal expansion, you can write elements of qp as Laurent series in p. So you can, with coefficients, these ai, which live between 0 and p minus 1. So you can think of this as like a base p expansion of an integer, except the powers of p can get arbitrarily large. And if you truncate this series at some power, then it will give you a legitimate integer. And because large powers of p are small in this norm, as you look at successive truncations, you're going to get a Cauchy sequence. And so, this is indeed a Cauchy sequence, which we added in when we completed it. So if qp is the Laurent series, then zp is just the power series. So again, it's series with these coefficients ai between 0 and p minus 1, except now the powers have to be non-negative. Equivalently, it's the unit ball in qp with respect to this norm. Because it's the unit ball, it's compact. And so that means that as an additive group, it has a Haar probability measure. And this Haar probability measure is very explicit. You can sample it by just taking these AIs to be uniformly random from this finite set, IID. And it's worth also saying that you have quotient maps from ZP to Z mod P to the NZ for any N, given by just throwing away all powers of P, at least P to the N. And this Haar probability measure, by these quotient maps, pushes forward to the uniform measure on these finite sets Z mod P to the NZ. And so it's also often just called the uniform measure on ZP. And pretty much everything that we do, you can sort of pretend that we're working over Z mod P to the NZ for large N, and then everything is finite probability. And a lot of people will sort of use this language instead when talking about p-adic random matrices. another group that we're going to talk about is the multiplicative group GLN-ZP, which sits inside GLN-QP, and it's a compact subgroup. It's in fact a maximal compact subgroup, and so it also has a Haar probability measure. And so both of these Haar probability measures are, we're going to use them to get random matrices that we then study various things about. So, in usual random matrix theory, you want to study eigenvalues or singular values typically. And so what's the analog here? So if I have some matrix in MnZp, let's say non-singular, then it's a map from Zp to the n to Zp to the n. So it has some image. This is going to be just some submodule of Zp to the n. And the quotient then will be a finite abelian p group. And so, this is called the cokernel of A. So to each of these non-singular matrices, you have a finite abelian p group associated to it. Now, by the structure theorem, this finite abelian p group will have the form just direct sum of z mod p to the lambda iz for some decreasing sequence of n integers, lambda I. And it's also true that you have an analog of singular value decomposition. So there will always exist matrices U and V in GLN-ZP such that, by multiplying on the left and right by U and V, you can get A to be in diagonal form with these powers of P on the diagonal. And these powers of P will be exactly the same lambda that you get in that, tell you the isomorphism type of this group, the cokernel of A. And so you can think of these lambdas as analogous to singular numbers, or analogous to singular values. So the main result that sort of started off p-adic random matrix theory was this result by Friedman-Washington in '87. And so they said, okay, for each n, let's consider an n by n matrix, which is random and such that the entries are IID, and each one is drawn from the additive Haar measure on ZP. And they computed the limiting probability that the cokernel of A is given by some given abelian P group of type lambda. And they found that this probability is some normalizing constant divided by the number of automorphisms of this P group. And this result is interesting because there are many directions you can take it. There's, from one perspective, this is a way of generating a random group. And there's been a lot of work in number theory for sort of different models of, random groups in more general settings. Like this is a random abelian P group, but, maybe you want a random abelian group, or, maybe you want some kind of random non-abelian group. And so there's this whole area of work on models of random groups of various types and sort of using them to model groups that show up in nature in number theory and combinatorics. So that's one direction that this has been taken. From another perspective, this lambda is a random integer partition. And so this sort of fits into the theory of random integer partitions. And, it turns out that this measure is actually a Hall-Littlewood measure. And so this, fits into the whole machinery of random partitions that we like in integrable probability. And from another perspective, this is a statement about random matrices. And so you can ask questions about how universal is this distribution? If we chose a different matrix AN, and it turns out that it's quite universal. So this result is sort of at the intersection of a lot of different, directions that have sprung out of it. And I should mention also that the original motivation for this was these heuristics for modeling the distribution of the p-torsion part of a class group of a random quadratic imaginary number field. And a lot of the interest in p-adic random matrices still sort of comes from number theory, from using them to model the distribution of some kind of group that shows up in number theory. As I said earlier, this decomposition is really analogous to singular value decomposition. And so for the rest of the talk, I'm going to write Sn of A to be this partition lambda. And I'm going to call these numbers lambda I the singular numbers, again, just by analogy with singular values. It's also worth noticing that because this distribution here stabilizes, because this limit makes sense as the matrix A gets very large, that if you have a very, very large matrix, most of these singular numbers are going to be 0. You're just going to have, a few non-zero ones, which are giving you this abelian group here. And this is very different from singular values where, if I take, say, a large Gaussian matrix, it's, the singular values are all going to be doing something non-trivial. So this is one place where this brand of random matrix theory kind of looks pretty different from the usual brand. So just a sort of recap of the structural picture that you should have in your head between this and usual random matrix theory. So in usual random matrix theory, okay, at least if we're looking at square matrices, you can think of these as a probability measure on the group GLNC if we're looking at complex matrices. Now, usually we don't explicitly require that the matrices be invertible, but they are invertible with probability 1. So you can consider this as a measure on a group. Inside this group, we have this maximal compact subgroup, the unitary group, and we have singular value decomposition where if I take matrices in this larger group, I can multiply on the left and right by entries by matrices in this maximal compact subgroup and get something diagonal with real numbers on the diagonal. And those are the things that we want to study. Over here, again, we have some big group. We have some maximal compact subgroup. We have some structure theorem that gives us a diagonal worth of random numbers, and we want to study those random numbers. It's also worth saying that often in real random matrix theory or complex random matrix theory, you want to study the Gaussian random matrices. And one very nice characterization of the Gaussian is often called the Maxwell characterization, is that the Gaussian random vectors are the only random vectors which have independent components and which are rotationally invariant. And similarly, for complex Gaussians, they are the only ones which have independent components and are unitarily invariant. You actually have basically the same characterization of this additive Haar measure as a measure on QP, namely vectors of IID Haar elements are the only random vectors which are invariant under this compact group GLNZP, which you should think of as analogous to rotations and which have independent components. So a good analogy to have in mind is that this additive Haar measure is like the analog of the Gaussian in this setting. And so these matrices with IID additive Haar entries, these are the analogs of the Ginebra ensemble with IID Gaussian entries. Okay, so any questions about that before I start talking about the more specific setting?
Maybe this is a very naive question. Is there any analog of the Friedman-Washington theorem for the usual random matrices, or doesn't make any sense?
Yeah, no, that's a good question, and the analog is the Marchenko-Pasteur law. So
I see.
yeah, like this Friedman-Washington is about the singular numbers of large IID additive Haar p-adic matrices, and the Marchenko-Pasteur law is about the singular values of large IID Gaussian complex matrices. So this is, you should think of this as exactly analogous to the Marchenko-Pasteur law. Yeah, good question. Anything else? All right. So I'm going to talk now more specifically about products of matrices. So in the complex setting, it's a quite old problem to study the singular values of a product of many, random real or complex matrices from some distribution as you multiply more matrices onto the product. So this is sort of a different limit than the usual large matrix limit that we often take in random matrix theory. And basically the first result here was this work of Furstenberg-Keston in 1960, where they showed that if you look at the log of the largest singular value of this product, then as the number of matrices in the product goes to infinity, you should see Gaussian fluctuations. And more recently, there's been a lot of interest in these matrix product processes from the sort of mathematical physics community. This is mostly in the past 10 years. And, there are lots of connections and applications to problems in statistical physics, dynamical systems, and some other things. There's also sort of a strain of recent work on matrix products within integrable probability by Ahn, Gorin, Strahov, and Sun, which use special functions and degenerations of Macdonald processes to study these matrix products. And the perspective taken there is pretty similar to the one which we're going to take with p-adic products, to sort of use symmetric functions to do as much as we can. And so in the p-adic setting, like let's suppose that I have some matrix A, it has some singular numbers lambda. This means that the determinant is going to be some unit in ZP times P to the sum of the singular numbers. So the analog here is that the determinant is the product of the singular values or the eigenvalues. And in the complex setting. And so this means that if I have a bunch of random matrices and I multiply them together, then because the determinant is multiplicative, the sum of singular values of this product will be the power of P in this determinant, which is going to be large because each of these matrices is going to give us some power of P, and then I multiplied a lot of them together. So this means that the sum of the singular numbers, lambda I, is getting bigger. But then it's still a question, I have some n tuple of numbers, and I know that their sum is getting bigger as I increase tau, the number of matrices that I'm multiplying. But what do the individual singular numbers look like as tau grows? And so a couple of reasonable guesses are that, they're all growing at basically the same rate, and they're all staying like pretty close together. Another possibility is that maybe they're like all growing roughly linearly, but at different rates. And so they're sort of spread apart from one another linearly. Another reasonable possibility is, maybe somehow when you multiply matrices, this helps the largest singular number a lot and doesn't really change the other ones. And so you might have the largest one just shooting off to infinity where everything else like changes by a very small amount. And it definitely wasn't obvious to me at first, and I don't think it should be obvious which of these three pictures you should expect from this product process. But luckily you can simulate it, and so you can actually see what it looks like in real life. So here I'm going to just set the notation that lambda of tau, which is some n tuple of numbers, lambda I of tau, which are the singular numbers. This will just be the singular numbers of the product of tau matrices. And so in this example, each of these matrices A are IID with IID additive Haar entries drawn from Z2, the two adic integers. And so you can see, so how to read this picture is, so for instance, if we look above 40, then these are the 4 IID matrices. And so the largest singular number is, about 50, and then the next one is like about 15, etc. And you can see the joint distribution of all of these as I keep multiplying on matrices. And so you can see here that they do seem to be spreading apart more or less linearly. So the second picture on this previous slide seems to be the correct one. And you can also see that these look like some kind of random walks, which, we have no idea how they're correlated with one another, or, what their distribution is. But, you can sort of see that it's reasonable to think of the singular numbers as you successively multiply on these products as, like, some n tuple of random walks, which are related somehow. And so then the question is, okay, what are these random walks? How are they related? What's the scaling limit of them? And so I'll tell you the result first, and then tell you sort of why it makes sense. So the result is that first, these random walks have a law of large numbers. So they're, you could see that they look like they're growing linearly. And so if you rescale them linearly, then they converge. The ith random walk, so the ith from the top, converges to 1 over p to the I minus 1. So, sanity check, as I is getting bigger, you're looking at lower random walks. And so, their limits should be smaller. And indeed, 1 over p to the I minus 1 gets smaller. So then the next result is sort of a functional central limit theorem. So if you subtract off this mean of these random walks, and so now you're looking at the random walk where you've rescaled time by this k, you've subtracted off the mean, and then normalized by root k times some explicit constant. So this is the scaling in Donskoy's theorem. Then as k goes to infinity, this is going to converge to a Brownian motion, a standard Brownian motion. And furthermore, the fluctuations of each random walk are independent of one another asymptotically. So you get the fluctuations just looks like n independent Brownian motions. So okay, this is sort of the main asymptotic result. And it turns out that it follows from actually sort of much stronger structural results that that hold true even at finite n. And to see what these are, I'm first going to shift perspective a little bit and think about these singular numbers, these random walks, in terms of a particle system. So I'm going to identify these n integers, lambda 1 of tau through lambda n of tau, with position of n particles on z. These particles can occupy the same location. And I'm going to define a discrete time evolution of these particles, which is going to model what happens when you take these matrix products. So to do that, I'll define what I'm calling here a basic step, and this is just a time step evolution of these particle configurations. So in such a step, each of the particles samples some random variable xi. It's a max of some difference of geometrics and 0. So in particular, it's not negative, but what it is right now, you shouldn't worry about too much. So each of them samples some random variable xi, and then tries to jump that many steps. So in this example, this one has sampled 1, this one has sampled 4, and this one has sampled 2. So now this one wants to jump 2 steps, this one wants to jump 4, and this one wants to jump 1. So this one here, we'll start with the one on the left. It can jump 2 and nothing bad will happen, no problem. So it just jumps 2. Now this next one, it wants to jump by 4, but that would cause it to pass the next in line particle. And we want these particles to stay interlacing. So what happens then in this basic step is that if you have a particle which wants to jump past the next particle in line, then it will jump as far as it can without violating interlacing, and then it will donate the rest of its jump to that particle. So this one was going to jump by 1, but now it's been donated the two extra jumps from this particle here, second particle, and so it now will jump by 3 instead of by 1. So this is a quite simple evolution, and in particular, particles which are far away don't affect one another at all. The only way that particles can affect one another is by literally colliding with each other. So this is, similar to a lot of particle systems, like Timestep, for instance, in that way. And so the result which relates this to matrix products is that, so take some partition lambda. Now there are two things that I can do with it. One is that I can take a matrix whose singular numbers are given by lambda, and then this matrix A, and then multiply onto it a matrix B, which is random with IID additive Haar entries, and then look at the singular numbers of the product AB. So that's one way I can get a new random partition. The other way is I can take lambda and then I can evolve it by a sequence of basic steps, which have parameters p inverse, p to the minus 2, p to the minus 3. So here, remember, these parameters enter the definition of the basic step just in terms of what this geometric random variable that's getting sampled is. And so in particular, if x is very small, then these xi's are going to be 0 with high probability. And so even though I'm saying evolve by an infinite sequence of basic steps, all but finitely many are going to not involve any actual jumping. And so this does actually make sense. And so the result is, I have two ways of starting with lambda and then having the positions of the particles change somehow, one by random matrix theory and one by these basic steps. And the result is that they give the same thing in distribution. And I claim that once you have this, at least conceptually, the limit result is basically, within your reach, because in this limit result, we were considering a product of many of these matrices. And, we looked at these random walks and, we wanted to say, okay, what are their limits? What are their fluctuations? What I've just told you here is that when I take these products of matrices, what the singular numbers are doing are just executing random walks, which are, well, first of all, the step distributions are the same for each matrix that I multiply on. And second of all, each singular number evolves independently of the others, provided that, they don't actually ever equal one another. So those random walks in the picture were actually evolving independently, except when they collided. And third point is that the largest singular number will have, on average, larger steps than all of the others. So this is because of this p to the I minus 1 here. This means that when I is small, xi has a larger mean. And so the random walks which are already ahead will jump further on average. And so this is what leads to this spreading behavior that you saw in the picture. The ones which are already ahead are jumping further. And so this means that in the limit, they're not going, they're going to all be very far away. And then because they don't interact except when they collide, you just have a bunch of independent random walks, which are far away from one another. And so sort of once you justify that this is actually what's happening, then you can just apply Donskoy's theorem to it immediately, and you get this functional central limit theorem. So once you have this random walk description, sort of the path forward is clear. But then a reasonable question to ask is, okay, where did this random walk description come from, right? Like this sort of seems like a much simpler description of this operation of taking matrix products than you would have reason to expect. Where does this come from? So where it comes from is, where we finally get into these these structural results and stuff with symmetric functions. So any questions about the last section before I get into that?
I have a question. So now it seems that you want to explain why basically this singular value lambda basically performs this this sort of push task. But so basically, let me see if I understand. So if you take a product of tau matrices, the dynamics runs for times tau.
Yeah. So
for theta.
So well, it will be tau iteration. It will be tau steps, but then each step is composed of this infinite sequence of basic steps where they sort of, the jumps get more and more likely to be small or trivial. Yeah. And so, it's a bit, yeah, it's a bit more complicated than just tau time steps.
Okay, yeah, no, so I didn't understand this part because if it was that because otherwise it would seem that that's really the product of one or more matrix then it just evolves the system for one extra time, but that's too simple.
Yeah, it's so it actually if instead of these additive Haar matrices I were taking n by n corners of n+1 by n+1 elements that were from the group GLN ZP with Haar measure, you know, because this is a compact group, then for those matrix products, it would actually just be a single time step. But somehow it's actually more complicated with these IID additive Haar matrices, and I've stated this result for those just because it's sort of the, you know, in some sense the simple case and the one which was studied by Friedman-Washington, but actually this, you have an evolution like this for much for more than just these additive Haar matrices, and it's actually simpler for corners of multiplicative Haar matrices, and then you don't have this whole infinite sequence of steps thing. And in particular, when it's an n by n corner of an n+1 by n+1 matrix, you actually just have a single step per product. Yeah.
In this case, okay, maybe it's getting too long. Okay.
No, don't worry.
I was thinking that in this second case that you described, that this dynamics is simply the fact that the determinant is the determinant is
multiplicative.
Multiplicative.
So the fact that the determinant is multiplicative tells you something about the sum of the singular numbers, but it doesn't tell you what the individual singular numbers do. I would really like it if there were a way to see this result straight from just sort of hands-on random matrix theory, or maybe not even random, just, you know, like hands-on linear algebra with these matrices, because it's a quite simple result. I feel like in principle, maybe one should be able to do it, but the only way that I can see this is sort of by building up this whole machinery with Hall-Littlewood polynomials and then using explicit formulas for Hall-Littlewood polynomials. So yeah, and this is a thing I've thought about, but I don't know how to see it, and I think it would be great if someone could.
Some sort of a refined multiplicativity.
Yeah, exactly. Yeah. And yeah, it kind of feels like you should be able to see this, but I don't know. I haven't been able to. Anyway, good question though. Anything else? Okay. So to understand the product of many matrices, you know, it seems reasonable that maybe a good first step is to understand the product of two matrices. And so you can think of this as, you know, this is very related to the sort of classical Horn problem, where, you know, this problem asks, let's say I have two matrices, and you know the singular values, or their p-adic, the singular numbers, then what are the possible singular values or singular numbers of their product? And this was sort of a very classical problem. And what I think is a quite cool fact is that both of these problems actually have the exact same answer. You can get any nu which satisfies some set of inequalities involving the parts of lambda and mu, and this is the same inequalities in both the singular value case and the p-adic case. They're these Horn's inequalities, and they show up in lots of places.
And the same as in some kind of representation theory question as well, right?
Yes, yeah, they're also the same ones that tell you when Littlewood-Richardson coefficients are positive, and also when what eigenvalues of sums of Hermitian matrices you can get, and a couple other things too, I think. Yeah, they show up everywhere. And so the deterministic versions of these problems kind of have the same answer, but then the randomized versions are different. So in the randomized version, you say, okay, let's take A and B, both random, but having some fixed singular numbers, lambda and mu. So you can think of these as sort of diagonal matrices with entries p to the lambda and p to the mu, then randomly rotated somehow, and then multiplied together. And then you can say, okay, what is the probability distribution on the singular numbers of A, B? So this is more or less the question that we want to ask. And to answer it, it's good to introduce these Hall-Littlewood polynomials. So these are, there's some family of symmetric polynomials in n variables indexed by partitions of length n, length at most n. They form a basis for the ring of symmetric functions. And so here I'm going to take t to be a real parameter, not just some formal indeterminate. And because they're a basis, if you multiply two of them, you can expand it in this basis, and it has some coefficients, these c lambda mu nu of t, which are called Hall polynomials. These are analogous to Littlewood-Richardson coefficients here. And if you just plug in some real numbers for the x's, in this case, we'll take this geometric sequence in t, and then divide out by this left-hand side, then you have a sum of real numbers which is equal to 1. And it turns out that if t is in this 0-1 interval, then these real numbers are actually going to be positive or non-negative also. And so you can use them to define a probability measure on these partitions nu of length n. This probability measure, it's worth reiterating, depends on mu and on lambda. So this is some sort of randomized convolution of the point mass at mu and the point mass at lambda. And the result that sort of underlies this whole business that I talk about today is the fact that this sort of Hall-Littlewood randomized convolution of lambda and mu is exactly the same as what you get if you take random p-adic matrices with singular numbers lambda and mu, which have distribution given here. So this is the same as saying that they're invariant. They're invariant under multiplication by GL and ZP. So it's the same as if you take these two random matrices and then multiply them together and look at the singular numbers of their product, where here t is set to be 1 over p. And so this result sort of wasn't in the p-adic random matrix theory literature, but it's in some sense actually equivalent to a quite old result, which is actually in Macdonald's book. So he sort of proves results about the structure theory of this Hecke algebra of the pair GLN QP and GLN ZP. And if you take this result about functions on these groups and sort of translate it into probabilistic language and move a couple of constants around, you get exactly this. So this is just sort of a translation of Macdonald's structural results into random matrix theory language in some sense. And it's, you can use this result to recover a lot of the things that that people had done in the p-adic random matrix literature. So one of these is that if you look at a rectangular corner of a hard distributed element of GLD ZP, so here here we're not talking about these IID additive Haar matrices anymore. We're talking about the Haar measure on this compact group, just as a group. So if you look at this n by m corner of such a matrix, then its singular numbers will have some distribution, and that distribution is exactly a Hall-Littlewood measure where the specializations are given by these geometric series and T's, often called principal specializations. And this Q is, it's just a dual Hall-Littlewood polynomial. It's proportional to P with some constant that you can write down. And the way that you get this result from the result on products is in the previous result. So we had this matrix A and B with some fixed singular numbers, and then we multiplied them together, and we had a result about the singular numbers of their product. But as a sort of limiting case, if A and B were randomly rotated projection matrices, then when you multiply them together, these projection matrices are just going to sort of cut off, cause to be zero a bunch of matrix entries and leave you with a corner. So you'll have this projection. When you take AB, you'll have this projection times V1 times U2 times this other projection. And so what that will leave you with is the top left n by m corner of this matrix, and then times some things on the left and right, which, because they're matrices in GLD ZP, they don't affect the singular numbers. And so by sort of taking a limiting case of the previous result, which turns out to involve some combinatorial difficulties in practice, but you can make sense of it, you exactly get this result about corners of Haar matrices. And it's okay, I said this already, but this measure is a Hall-Littlewood measure, and as special cases it includes, well, not this specific one, but these Hall-Littlewood measures generalize the Schur measures, and they're a special case of Macdonald measures, and they show up in lots of places. And so this was a result about corners of Haar distributed matrices. But then you can say, okay, well, what if I take an n by m corner, fixed m and n, of a Haar distributed, multiplicative Haar element of GLD ZP, where D is very, very, very large. As D gets very, very large, the entries of this n by m corner are going to become basically independent of one another, and their distribution will approach just these IID additive Haar, this IID additive Haar measure. The analogous fact in the complex case is that if you take a very, very large unitary matrix and you look at a corner and you rescale appropriately, this corner will look like an IID Gaussian matrix. This is also a true fact. And so this means that by taking a limit of the previous result, we get this result that the singular numbers of additive Haar matrices are also given by a Hall-Littlewood measure. And in particular, this using explicit formulas for Hall-Littlewood polynomials, you can recover the results of Friedman-Washington. You can also recover, a bunch of other formulas in the literature. And you have to know what a formula is for this number of automorphisms, and what explicit formulas are for these things, but these are all written down. And it had been noticed before that these measures which were appearing, for instance, in the Friedman-Washington results, were special cases of Hall-Littlewood measures. As far as I know, this was noticed by Jason Fullman in 2016. And he sort of noticed it by, taking explicit formulas and computing both sides, but there wasn't really a sort of conceptual explanation that I could understand for why Hall-Littlewood measures should be showing up here. And here we sort of have what I think is a pretty natural story, where you start with this result of Macdonald that describes matrix products, and then you can basically derive every appearance of Hall-Littlewood polynomials in this business from that result. So I think this is sort of a conceptually appealing story. Okay. And so just a word about where the particle system comes from. So using just sort of general machinery of Macdonald processes, it follows from these results that if you look at the joint distribution of the singular numbers of a product, where here, this is the joint distribution as tau, the number of matrices in the product varies, then this is an ascending Hall-Littlewood process. And because we have explicit formulas for these Hall-Littlewood polynomials, we can actually sort of write down explicitly what the transition density in this Markov chain that you get from multiplying on more matrices, we can write down explicitly what this is. And then if you sort of take this formula and stare at it for long enough, you'll see that it seems to be coming from an interacting particle system like the one that I showed you. And then you just sort of check that this is the case. And this is sort of difficult to communicate because it really just requires staring at formulas for a while, but hopefully it's believable and you can take my word for it. And that's in essence the only step in the proof of that asymptotic result that I haven't gone over here in some way. We had these exact results. We had various limiting cases of them to get to products of Haar matrices. Now that brings us to the particle system. And then once you have the particle system, you just sort of had a Donsker argument to get to this limit. So it's a reasonably straightforward chain through all of these things. So in my last 5 minutes, let me just talk about the structural analogies between this business and the singular values, which is, so I've sort of been trying to highlight these analogies throughout the talk, but they're particularly nice within this symmetric function framework. So just a reminder, the Macdonald polynomials, there's some other family of symmetric polynomials. They have an extra parameter q, and when q is 0, they're the Hall-Littlewood polynomials. But for general q and t in this interval, they have the same positivity properties that let you define these measures. Not just the usual Macdonald measures, but also measures coming from products. So you can define these Macdonald measures. This is some measure on partitions. It varies in q. As you send q to 0, you get the measure that we saw before, which gives you the singular numbers of an n by m corner of a d by d Haar matrix. This was the result we saw before. In another limit, if you take t to be a power of q, a very specific power of q, and then you send q and t to 1, and you also rescale lambda somehow. And in this rescaling, lambda will become, instead of a partition, it will become a tuple of real numbers. Then this actually gives you the singular numbers of an n by m corner of a d by d matrix drawn from either the orthogonal unitary or symplectic group with Haar measure. So these are, this is the same picture, an m by m corner of a d by d Haar matrix, but in this limit, it's the p-adic version, and in this limit, it's, the real complex or quaternion version. But these are both limits of exactly the same measure at the Macdonald level. the same sort of parallel is true with this product measure. So you can again define a measure. If you fix lambda and mu, you can define a measure on nu in this way. And I should say, because when I gave a similar talk, Vadim Gorin called me out on this, that we don't actually rigorously know that this is a probability measure. We don't know that these things are positive yet, because we don't know that these Littlewood-Richardson coefficients are positive for general Q and T. However, in these two limits, we know that these are positive, and we're pretty sure that these ones are positive too. We're pretty sure that this is a probability measure, but caveat, we don't know this. But anyway, as you take Q to 0, you get this measure which described the product of two random p-adic matrices with fixed singular numbers. As you take the exact same other limit as before, you get a measure which describes the singular values of the product of two either orthogonally, unitarily, or symplectically invariant matrices with fixed singular values which come from the appropriate limit of lambda and mu as these sort of rescale into real signatures. So just to sort of recap this story, like what did we do here? So we had these exact results for p-adic matrix products, p-adic matrix corners, and additive Haar matrices, the singular numbers of these. And these all were sort of expressed via Hall-Littlewood polynomials, and they all came from this structural result of Macdonald, which sort of told us how to do products, and we could derive everything from that. These, using explicit formulas, these gave us this interacting particle system description of the product process, and then this was used to get these analytic results, the law of large numbers and functional central limit theorem. So the takeaways here, I think, should be that in this symmetric functions based perspective, p-adic random matrix theory and complex random matrix theory look basically structurally the same. This is what I've been trying to highlight on these past two slides. Like everything you look at looks exactly the same. You just plug in a different family of symmetric functions. And just because these are structurally the same doesn't mean that they sort of look the same on the ground. Like we saw, the Marchenko-Pasteur law, as you pointed out, Cheyenne, this is some continuous probability measure on R, whereas that measure in the Friedman-Washington result, this was some very discrete measure on abelian P groups. So on the ground, these things may look quite different, but still at the structural level, they look like the same thing in terms of symmetric functions. And this is a very useful guide for figuring out how to prove things and sort of what you should expect. This, on the singular value side, this symmetric functions Macdonald process-based approach has already been very useful in proving asymptotic results. I mentioned these results of Gorin, Strahov, and Sun. And here it's been quite useful for proving similar things about p-adic matrices. But I think, there's been basically no study of p-adic matrices from this sort of integral probability-esque perspective. And so I think there's a lot of room to take this perspective and sort of see how far you can push it in p-adic random matrix theory. And this structural analogy provides a very good guide for sort of what are reasonable questions to ask and what you can expect of them. So that's all I have. Thank you guys for your attention.
Oh, thanks, Roger, for the talk. So if anyone has questions, they can unmute themselves. So I have a few questions. So you showed like there are exact formulas when for the singular values when n and p are n and the tau are fixed, right?
Yeah, I didn't show the formulas. So
Yeah.
this result is sort of in the large, for square matrices in the large n limit. There are exact formulas for finite n also, even going back as far as Friedman-Washington.
Mm-hmm.
Um,
So I'm thinking like, can we do something like n tends to infinity and tau tends to infinity together? Because there are some analogs for the GUE case as well, like other kinds of limits.
yeah. So yeah, so definitely in the complex setting, yeah, these simultaneous limits have been studied. Like I know Andrew has done work on these simultaneous limits. I think that in this setting, so in the complex setting, once you get this sort of once you get to this result, then to do the asymptotics, they use Macdonald operators to sort of get observables and then study these observables. And here, because these observables kind of become degenerate, and there's still ways to deal with them, but you sort of have to, things get a little bit weirder in the Hall-Littlewood case than they are in the limit that gives you like complex matrices. So sort of because I had these very explicit formulas, I could just like write down this particle system and then kind of do things in a bare-handed way. And I think it would be more difficult to adapt that to the simultaneous limit. But I think we do still have ways to study Hall-Littlewood processes using these Macdonald observables. And, if I haven't tried, but it seems very possible to me that you could recover these results and maybe also study those sort of simultaneous limits if you took that approach instead.
See.
Yeah.
So a stupid question. So the parameter t is I'm guessing here, but is it 1 over p?
Yeah, it's still 1 over p. Sorry, I should have said that. Yeah.
And so of course you're studying the Hall-Littlewood case. Is there any like p-adic random matrix theory for Q-Whittaker polynomials? Q-Whittaker measure?
Yeah, so I don't think so. The thing that I know of that is vaguely relevant is well, actually the only place that I know of where Q-Whittaker functions sort of show up in nature is I don't know if you remember in one of these discussions after the lattice models seminar, Borodin mentioned this paper where they do things like Schur-Weil duality and Howe duality, but
yeah,
for
by
groups.
Fagin.
Yeah, that one. Okay, the reason that I'm saying that this is somewhat similar to what I've done here is actually all of these results still hold if you replace ZP by FP double brackets T and replace QP by FP double parentheses T. So like rational functions in T. It turns out that these results are sort of simple enough that they don't see the characteristic of this field. They only see the size of the residue field. And this stems from the fact that the structural result of Macdonald on which this is based works for any non-Archimedean local fields of size, where the size of the residue field is 1 over T. And so this this makes these two, this makes that Fagan and whoever the other person paper sort of somewhat similar to this business in my mind, because you can think of them both as results about groups over FP double brackets T. But that's I think all that I can say about the possible, like where you might look for appearances of Q-Whittaker functions in this business. I certainly don't know of anything more concrete than that.
So a question that is, sorry, unfortunately not related to your talk, but what about these whole polynomials? Of course, there is the chapter on Macdonald's book, but like, does there exist a combinatorial characterization?
Yeah. So these whole polynomials tell you they count the number of, okay, so let me just go back to
I don't want to put you on the spot.
No, I can, I don't remember exactly whether it's the Hall-Littlewood, whether it's the Hall polynomial or whether it's like normalized in some way. But what they do is they count the number of, so this Hall polynomial depends on these partitions lambda, mu, and nu. So basically this counts the number of short exact sequences that go 0, abelian p group of type lambda, abelian p group of type nu, abelian p group of type mu 0. Or in other words, you know, the number of subgroups of an abelian p group of type nu, such that the subgroup has type lambda and the quotient has type mu.
And this is where they show up.
Yeah, this is exactly where they show up. And this leads to their showing up in p-adic random matrix theory because the cokernels of these matrices are finite abelian p groups. Like these are sort of these are equivalent appearances of Hall polynomials, I guess I'll say. So yeah, that's the combinatorial story with Hall polynomials, up to, you know, remembering what this normalization is, and, you know, are you counting these short exact sequences up to automorphism or not, which I don't remember off the top of my head.
But if you want to get the Q-Whittaker polynomials, you can take the analytic continuation with respect to n. But it doesn't make sense.
Wait, with respect to n, why would that give you Q-Whittaker?
That doesn't it give a Q-Whittaker? Well, so there will be some polynomial, some because it is the fusion.
Okay, yeah, I don't remember off the top of my head how the to Q-Whittaker fusion works. So I remember that this exists. So, you know, maybe you can get something by this sort of analytic continuation.
And then there is the analytic continuation with respect to the dimension of the, with respect to n. It does.
Right. Which, yeah, I mean, there are lots of interesting limits of these measures you can take, which, you know, completely lose any relevance to p-adic random matrix theory. Like, you know, the t goes to 1 limit is interesting, but that, you know, there is no z1, so that doesn't, you know, that doesn't tell you anything about random matrices. But yeah, I mean, maybe you'd get some kind of interesting Q-Whittaker particle system if you do this kind of analytic continuation. I don't know. I have no idea.